So section 10.5 is actually much simpler than they make it out to be in the chapter. This is really just about polarity, which means a partially negative and partially positive side of a molecule. So if we look at the Lewis dot structure for hydrogen monochloride or hydrochloric acid, depending on how you look at this, but we're going to look at the covalently bound version, so hydrogen monochloride. The electronegativity of the chlorine is much greater than the electronegativity of the hydrogen. So because of that, the chlorine will actually pull electrons from the bond closer to it and farther away from the hydrogen. What this does is this makes the hydrogen slightly positive, and that's this little lowercase Greek delta symbol, and it makes the chlorine side slightly negative. And we can draw this in our Lewis structures, or actually in our shape structures, so this linear molecular geometry, by drawing lines from where the electrons are coming from towards where they're going to as a vector, a mathematical vector. If something is matching electronegativities, like two molecules of the exact same sort in a particular bond, then you're not going to have a draw from one direction to another. So you have no net pull of electrons, and therefore you have no polarity, no partially positive and partially negative side. Let's look at a couple more examples. We have hydrogen monochloride gas. That's the covalent version of HCl. We have hydrogen being less electronegative than chlorine. So we have polarity making this a polar molecule with a negative side by chlorine and a positive side by hydrogen. For ammonia, we have a tetrahedral electron geometry and a trigonal pyramid molecular geometry. The vectors for the hydrogen towards the nitrogen pole of electrons gives us a net direction of upward towards the nitrogen. So if you add all of those mathematical vectors together, here's your net dipole. So we have a partially negative on this side, and somewhere amongst the three hydrogens we have a partially positive side to the molecule, making this a polar molecule. Now with boron trifluoride in a trigonal planar arrangement, we actually have the case where these two vectors towards fluorine are net opposing the vector to this fluorine. And this fluorine is net opposing these two vectors to fluorine. And so on each side, to where there's a symmetric pull in all three directions which cancel each other out. So even though the individual bonds are polar, so we have polar boron to fluorine bonds, the overall molecule itself is nonpolar. Same thing happens with a tetrahedral arrangement. If all the atoms are the same, all of these individual net poles will be opposed by a pole on the opposite side and cause canceling. So that makes carbon tetrachloride nonpolar. But if there's a single chlorine with 4 hydrogens on chloromethane, for instance, then the net pole will be from hydrogens towards carbon, carbon towards chlorine, so a net pole upward. Now, even if the hydrogens were pulling downward, though, they wouldn't be the same amount of pull because their electronegativity is different. So anytime we have non-symmetry in a molecule, that's the key. Symmetry. That's going to make it polar. If we have a molecule that's completely symmetric, that will be a non-polar molecule because we won't have a net higher negative, lesser negative side. And that's pretty much it for polarity.